All right, thank you. So yesterday, we gave an algorithm to compute Coleman integrals. Between points in different residue disks. And this was on hyperelliptic curves. And the method was something that we called, so I don't think we said this yesterday, but David said this morning. This is analytic continuation along Frobenius. So just to recap what happened there, so we wrote down action Frobenius on some differentials and factor basis for H1 Jerome. And then once we wrote down that action, we introduced these very large pole orders. So then we had to reduce pole orders. And at the end of the day, we got something that was nice. So an expression. So Frobenius here is this map phi. So phi per star omega I is some dhi plus linear combination of our basis. And this is, of course, work of Chabauty. Then once we had that, we wrote down, then wrote a linear system to produce the values. So some vector of values of the Coleman integrals between our points on all of our basis elements. All right, so that was a recap of the end of yesterday. So now we'd like to do this for more general curves. So how do we do this? So one of the key ideas in this algorithm was that we had some reduction algorithm. Once we computed the action of Frobenius, we had a systematic way to reduce pole orders to get ourselves into this expression. And as I mentioned earlier, this is due to Chabauty and his work on computing zeta functions of hyperelliptic curves. So the idea is if we have such an algorithm to do this for more general curves, maybe we have some hope of writing down a Coleman integration algorithm as well. So Tautman did this a few years ago. So here we'll suppose we have x over q, a nice curve of genus G with a plane model of the following form. So we want it to be monic in Y. And we want it to be irreducible. And we want these polynomials in X to have integer coefficients. And we'll suppose that P is a good prime for our curve X. So this is a sketch of what Tautman does in his algorithm. So he considers the map from the curve to P1. So this is a map of degree d sub x. And he removes the ramification locus. And to kind of make the analogy of what, how this compares to what is happening in Chabauty's algorithm, this is the analog of removing the Weierstrass points. And then we choose a lift of Frobenius that sends x to x to the p. So all this is p power Frobenius. And then we compute the image of y through Hensel lifting. And then we compute our various bases of cohomology. So we compute a basis of H1 rigid, and we have some comparison theorems that tell us that this is essentially H1 de Rham. But we do this using integral bases of function fields. And this is something that is in magma. So this, having everything in terms of integral bases, really helps with the bookkeeping. All right, then this plays a role here when we compute the action of Frobenius. On our differentials, and we reduce pole orders, again using our various relations in cohomology. And here another zeta function algorithm comes into play, some work of Alan Lauder. So Lauder's vibration algorithm. And here Tautman uses the integral bases as well. Okay, and then once we have all this, then we have an expression, again, phi for star of omega I is some dhi plus our matrix of Frobenius, and then we use this to give a linear system to produce the values of your various Coleman integrals between different residue disks. Okay, so just to kind of illustrate how this might give us some interesting information, so Jan and I computed this example. So we can compute some 7-adic Coleman integrals on a non-hyperelliptic genus 55 curve, just for fun, to show, as you do, right, to show that its Jacobian has positive rank. And this took about a day. But I was curious to see if we could push this algorithm in higher genus, and that kind of seemed to be the extent of what it was happy with. So if you're curious about this, you compute. So we were able to find such a curve in magma. Magma can generate some random plane curves, and we searched for some that had some rational points, so that kind of forces a bit of extra structure. We computed some Coleman integrals between those rational points, and then we looked at the values of the integrals of the regular one forms, and we found that they were non-zero up to some p-adic precision, and so that told us that we had some positive rank. Okay. So now let me say something about iterated integrals. So we'll want to look at iterated integrals in non-abelian Chabauty. So the x still be a nice curve of genus G. And by work of Coleman and Coleman Dirichlet. We have a theory of iterated p-adic integrals on X, and more generally for higher dimensional varieties as well by work of Besser. So what are these? So these are iterated path integrals. So I'll typically denote them with one integral, one of these symbols, and I'll have a collection of differentials, so say eta n through eta 1. And what this means is I'm iteratively integrating, so say to some dummy variables here, and rewriting each of the differentials like so. And these are the p-adic analogs of the iterated integrals of Chen. So typically, when I write an iterated integral, so this n-fold iterated integral, there are a number of integrations that are happening along the way, but I'll typically just suppress those integrations and use one integration symbol. All right, so just to kind of be clear about what that means, so in our computations, we'll focus on the case n equals 2, the double Coleman integrals. So these are things that look like the integral from p to q, some eta 2, eta 1. And what I mean by that is, well, we're integrating p to some dummy variable r, and we get some expression in terms of r, and then we rewrite eta 2 in terms of this dummy variable r, and then integrate out from p to q. Okay? So these integrals play an important role in non-abelian Chabauty. So we saw that one of the arrows in the usual diagram is in terms of these iterated Coleman integrals. So what I'd like to talk about is how to compute these iterated integrals, and then just tell you a little bit more about where some other contexts in which they apply. And in particular, in the case of double integrals, their relationship to p-adic heights. All right, so how do we compute them? So we want to apply an algorithm for computing action of Frobenius on p-adic cohomology. So for instance, Kalaya or Tautman, as we discussed, and this produces the usual expression which we now iteratively use. And we observe,
So I have a question.
yes?
So are both of your eta 1 and eta 2 of the first kind?
We will allow for forms of the second kind as well, and then we need to be careful about, say, tangential base points. So if we allow for a pole, but a zero residue, but say a pole, for instance, this will happen if we were to consider the full basis of H1 de Rham and consider various words in that basis. Then we need to be careful about our endpoints. So absolutely, thanks for bringing that up. Of course, the simplest case would be if we could just restrict to regular one forms, but we will need to consider forms of the second kind as well.
Another question.
Yeah.
In the starred equation,
Yes.
are the keys chosen so that they're uniformizers at P and not value 1 at Q or something?
So locally, if we were doing this in a single residue disk, then certainly we would pick a uniformizer at P or Q, and then that's what you would do. You'd kind of, you'd rewrite each differential in terms of that uniformizer and then formally integrate. I'll kind of describe what happens for the case of a double integral if you need to go between different disks. So it's kind of a formal variable that, it's not necessarily a uniformizer. But,
I'm just trying to figure out the dependence the right-hand side has on P and Q. It's somehow in the T.
Yeah, so certainly I think maybe the first sort of iterated integral you should think of as a tiny iterated integral. And then absolutely, as you said, you're picking a uniformizer at P or Q and then rewriting in terms of that. Anything else? Okay. So, we want to apply an algorithm for computing the action of Frobenius on cohomology to produce this. Maybe I'll say iteratively. Basically, for every differential, you want to apply this action of Frobenius and then reduce in a certain way. One thing that helps you reduce is to observe that the eigenvalues of the matrix of Frobenius tensored with itself and times, they are not 1. So in a similar way, you can invert the necessary matrix and reduce the computation of n-fold iterated integrals to n-1-fold iterated integrals. Just like we saw already for the case of the single integrals, we reduced a lot of the computation. So once we could invert this matrix, the other thing that we used was the fact that we knew the fundamental theorem of calculus, and we could integrate df to pull out some constants. So we will reduce our double integrals to some values of single integrals in this matrix inversion. So here are some useful properties of iterated Coleman integrals. So I'll let omega I1 through In be forms of the second kind, but I'll, just to kind of keep things simple, require them to be holomorphic at the endpoints. And so the first thing is that if I integrate from P to itself, this is still 0. If I want to sum over all permutations, sigma, where I permute all the indices here, so this is now a product of single integrals. And if I have an integral from P to Q, and I want to swap the endpoints, well, I also have to correct for that. So I have a -1 to the n here, and I have to reorder the integrand. Okay, and then lastly, something to break up the path, so P, P prime, and Q. again, with all differentials holomorphic at each of these 3 points. Then if I integrate from p to q, omega I1 through omega IN, this is the sum p prime to q of omega I1 through omega ij. And now we're breaking this up, so we have this sub-integral here, omega ij plus 1, omega in. So this last one break up a path. Okay, so with this gives us the analog of additivity and endpoints. Additivity for our double integrals. So there are more terms involved, but there's not too much that's different here. So if I have, so if I'm integrating from p to q, but I'm introducing this third point p prime, so I go from p to p prime, omega I, omega k, plus p prime to q prime, omega I, omega k. Oh, I don't have a q prime. Sorry. Okay, so now I actually have p prime, q, All right, so p prime to q prime, omega I, omega k, plus q prime to q, omega I, omega k, plus several products of single integrals. All right, and then now to write down a linear system to compute values of double integrals, we want to take p prime to be Frobenius on p and q prime to be Frobenius on q. And here's how we compute double Coleman integrals. So we have Frobenius on p, Frobenius on q of some differential omega I, omega k. And we want to pull back by Frobenius. So this is Frobenius on omega I, Frobenius on omega k. And then we separately, so for each differential, we apply an algorithm to compute the action of Frobenius and get an expression of this form. And if we move things around and simplify this, we get some values, CIK, in terms of some single integrals, plus essentially this tensor product of M with itself. And so this CIK, so these are things involving single integrals. And in the notes, this is spelled out in a bit more detail. And if we move things around and add some other correction factors, what this gives us. So all of our double integrals on our basis. So now we have a big matrix here. So matrix of Frobenius tensored square minus 1. And then our CIK, and then some tiny double integrals. So from phi of p to p, omega I omega k minus p to q omega I, so just some products of single integrals minus another product from q to phi of q omega I phi of p phi of q omega k plus one last tiny double integral. All right, so the point is to say we can write these things down, we can implement these on a computer, and we can get some numerical values out of all of this. So the linear algebra is not so tricky, it's just a matter of writing things down carefully. Where this is going is so a preview of an application in the quadratic Chabauty realm. So if we're able to compute all of these double integrals, then we might be able to use them to understand rational or integral points on curves, since that's what we're trying to do. So let me introduce the following setup. So we're going to have E be the minimal regular model of an elliptic curve. And we'll let x be the curve minus the point at infinity. And we'll take omega naught to be the invariant differential dx over 2y plus a1x plus a3, the usual Weierstrass model. And omega 1 will be x omega naught. We'll need to introduce a base point, so possibly tangential, either. So there's a little bit more about this in the notes, and I imagine this will also come up in some of the other lectures. So a tangential base point at the point at infinity, or you can just think of, if you have one, an integral to torsion point. And we'll let P be a prime of good reduction. And we'll suppose that E has analytic rank 1. And to simplify things, Tamagawa product 1. Okay, then, so with all that, we'll let log be the usual thing. So the integral from B to Z. So here I'll allow Z to vary across the curve, so I'm not restricting to the disk at infinity. And D2 will be the integral from B to Z of omega naught omega 1. So here we have a double integral that really isn't so closely related to single integrals. And the theorem, due to Kim, and then we had some follow-up work with Kabaya and Kim, is if we have a point P of infinite order, then the integral points on this affine curve, x, this is in the zero set of the following function described using log in D2. So log of this one point that we know about squared times D2 of Z minus log of Z squared times the value of D2 on this point. All right, so this tells us that if we're able to compute D2, essentially looks like a dilogarithm, and log, and also the values of D2 and log on one known point, then we can write down some p-adic power series, look at it in each residue disk, collect its zeros, and that will give us some finite set of p-adic points that will contain the integral points on this affine curve. And of course, maybe you will need to do more work to actually recover the integral points. But this is maybe a glimpse of what we'd hope to do in the quadratic Chabauty method, to use some higher iterated integrals and write down certain nice combinations of them and get functions that will tell us some interesting arithmetic information. Yes?
Is there a sense of how big the zero set is?
So the question is there a sense of how large this set is? And I think we've written down, so Nitin Dagra and I have written down some bounds in some cases. In quadratic Chabauty, offhand, I can't remember. So they involve some, so they're polynomials in the genus. They take into account also the size of the curve over FP, and then some information at bad primes as well. So in the case of integral points, we can do that. So in the case of integral points on elliptic curves, we can do that as well. In practice, we could also compute this and just see how many zeros it has. All right. So Kim observed that, so while we were doing this was an exciting project to be involved with, Kim observed that this D2 is related very closely to a p-adic height. On the elliptic curve. All right, so the next thing I would like to talk about is p-adic heights on Jacobians of curves, and the relationship between some of these double Coleman integrals and p-adic heights on curves. All right, so why do you want to do this? Well, p-adic heights are a natural source of bilinear forms on global points. And they allow us to generalize some of our linear techniques from Chabauty-Coleman. And I should also remark that these p-adic heights also appear in a number of places in literature. So these are the same p-adic heights as in p-adic Birch-Slinnerton-Dyer and p-adic Rose-Sagier. And one of the projects aims to investigate using some ideas there to maybe say something about quadratic Chabauty. All right, so now X will be a nice curve of genus possibly 1, so 1 or more, and P is still a good prime. We'll have to make some choices at the start. So we're going to fix a branch of p-adic log. And also an Adele class character. Chi. And a splitting of the Hodge filtration on H1 drum. Such that the kernel is isotropic with respect to the product on H1 drum. So we'll take chi to be the cyclotomic character. And maybe to say a little bit more about what the splitting of the Hodge filtration does for us and why we need it. So a splitting of the Hodge filtration This corresponds to a subspace, a complementary subspace, the space of regular one forms in H1 de Rham. So fixing a splitting of the Hodge filtration corresponds to fixing a subspace W, the kernel of S of H1 de Rham, that's complementary to the space of holomorphic forms. So in other words, we have this, that H1 de Rham of X over QP is the regular one forms plus W. And we want this to be isotropic with respect to the cut product pairing so that we have a symmetric pairing for our height. So there are a number of constructions of p-adic heights in the literature. The one that I'll start with is due to Coleman and Gross. There's foundational work of Mazur and Tate, Neron, Schneider, among others. So to give the Coleman-Gross setup for Jacobians of curves, we first start with the cyclotomic p-adic height on degree 0 divisors. So this is a symmetric bi-additive pairing. So we make some choice of divisors. So D1, D2. We get some global height. So here we need to be careful about what sorts of divisors we allow. So D1 and D2 are degree 0 divisors with disjoint support. Okay, so it's a symmetric bi-additive pairing on degree 0 divisors on the curve such that the following holds. So this global height on divisors is a sum, a finite sum, or a sum over all finite primes. And it turns out that it will also be a finite sum, because many of these terms will be 0, but maybe that's later. So we fix some prime that we're working with, and so there's a distinguished local height at P, and we'll come back to that in a second, plus local terms away from P, so local heights HL. And now, what do each of these terms look like? So the local height at P is a certain Coleman integral, so an integral of a normalized differential of the third kind. So now we're going to allow for poles along D1, and we're going to integrate along D2. And the local heights away from P, on the other hand, these are sums of the form, so some intersection multiplicity. So this is some rational. Weighted by the p-adic log of the prime L. So if you've computed canonical heights on Jacobians, and you know that there's also a similar decomposition in terms of local heights as well, if you've computed these intersection multiplicities, these are the same things that you would see here. We're just weighting by the p-adic log now. All right, so for beta, an element of the function field, we have that h of, so the height of D and the principal divisor is 0. So we get a symmetric bilinear pairing on the Jacobian. And we get some p-adic values. So let me say now more about this integral omega d1 along d2. So this local height at p. So I said already that this has something to do with a Coleman integral. So we need to construct a certain normalized differential omega d1 with respect to our choice of this complementary subspace W. So we'll let T of QP be our third kind differentials. So here I'll mean that I want simple poles and integer residues. We have the residue divisor homomorphism. So we take one of these differentials of the third kind and we get back its residue divisor. So if I have some omega, this is a sum for all points, the various residues, and then I weight by the point. And this induces a short exact sequence and here is a residue divisor homomorphism, like so. And then what we want is that omega d1 will be a certain third kind differential with residue divisor d1. All right, so let me just give an example of what this looks like. So we'll let x be a hyperelliptic curve. And suppose I pick some points. So I'm going to write down a divisor, p minus q, p and q, non-Weierstrass points. And then if I write down the following, so dx over 2y, and then I want a pole at p, a simple pole at p, a simple pole at q, and I want a residue of +1 at p and a residue of -1 at q. So I want my pole at p, but not also its image under the hyperelliptic involution. So I add y plus yp in the numerator. And then same sort of thing here, but with a minus, x minus xq, y plus yq. So this has residue divisor d1. So in other words, simple poles at p and q, and residues +1 and -1 respectively, and no other poles. But you can see that we can add to omega any regular one form and still get d1. So this is a bit of a problem. We want to fix a particular one form. So I haven't said so much about how we're going to choose W. We just want it to be complementary to the space of regular one forms and also isotropic with respect to the product pairing.
So you have a y plus yp?
Yes, so a y plus yp in the numerator. So we want it to be a pole just at the point P, but not its image under the hyperelliptic involution. So if I allowed 1 over X, and then there's some cancellation. Okay. So yeah, I'll say more about W. That's a great question. Because we have to make some choice, and it's good if we have a nice choice for W. So adding any holomorphic eta to our omega and taking the res of eta plus omega also gives us D1. So must take care of this. All right, so we'll let TL of QP be the log differentials. So these are things that look like df over f for some f. And this gives us the following short exact sequence. So quotienting out the one over here by log differentials. And then here's how we normalize. So this is in the paper of Coleman and Gross, that there is a canonical homomorphism psi from third kind differentials mod log differentials to H1 de Rham, such that psi is the identity on holomorphic differentials, and it sends third kind differentials to H1 de Rham, so to second kind mod exact. And now we can define this omega d associated to a divisor. So if I have some divisor of degree 0, then omega d is the unique differential of the third kind with, so of course it has to have the right residue divisor, but also this map psi will send omega d into this complementary subspace. So here is one choice for the complementary subspace. If P is a prime of ordinary reduction for the Jacobian, then we can take W to be the unit root subspace for Frobenius. All right. So I think the next thing I would need to do is to integrate differentials of the third kind to give an algorithm for local p-adic heights. But I think that requires a bit more time, so I think I'll stop here. Thank you for your attention.
Questions?
Could you say a word on why HP D1, D2 is symmetric?
On why the local height at P, is it symmetric? All right, I don't know if I can do this quickly. Maybe we can do this after. So, yeah, let's talk after.
So in this earlier example with the elliptic curve, you wanted E to have analytic rank 1 and Tamagawa product 1. Is there any reason for this?
Yes, so analytic rank 1 because we wanted algebraic rank 1. So we wanted so this height, this quadratic form to be kind of in this one-dimensional space. And the Tamagawa product one, that wasn't so essential. That was just to kind of simplify the constants involved. So more generally, if you had whatever Tamagawa product you have, then you have some local contributions at those bad primes. And so the statement would be then that you have this function taking on some finite set of values that you can calculate ahead of time.
Okay, let's thank Jen again.